And connected with light, we have got the human eye. So this 5 minutes I'll switch it off. Okay, because there is some circulation, but it's very stuffy. So we know that magnetic effects is nothing but a continuation of electricity, current electricity. Once we are done with this, we come and take it up. So you should be comfortable with most of the chapters. Now, if you look at the chapter name or the chapter title, we know that the magnetic effects of electric current. Okay. So if you look at electric current itself, children, once I have started, I don't think there should be any discussion. There should be no talking, please. Okay, otherwise, I'll make you sit in each corner. That's all. I have no other option left. So when I'm talking about electric current, we have seen that one part of it is nothing but the heating effect. Okay. And which law is with respect to heating effect? Your current the previous level, Joule's law, correct? So we have seen that it is Joule's law of heating effect. H is equal to I square R. So that means to say whenever the current is passing through a wire, it has a tendency to get heated up depending upon the resistance and also depending upon the type of material that we are using. If the resistivity of the material is pretty high, we know that there is more kinetic energy. And when the electrons are moving, obviously the kinetic energy causes more contact, and that can increase the heat. Okay. In the previous chapter, we have also seen the type of material that is required. If you want a good conductor, then obviously it is meant for conducting electricity over long distances. That's when we are taking copper wire or aluminum wire. But if the same type of a material is used for, let's say, toaster or diesel, it's going to be of no use. So if at all we want heating effect, then obviously we have to use either an alloy or some kind of a substance which has got a high resistance. Now the other effect that we are talking about is a magnetic effect. So one is the heating effect and the other one is the magnetic effect. Okay. Now once again, if you want to go back in history and find out how it has actually come about. Okay. So it was basically because of some kind of experiments which Austin, if you look at the photo of Austin, he's supposed to be the father of magnetic effect of electricity. He was a Danish physicist, and I believe he was working in his lab with electricity. And by chance, he had what is known as a needle. What needle are we talking about? A magnetic needle. A magnetic needle, okay, which is kept. It was kept very close to whatever experiment he was doing. Now, what is a magnetic needle? It is nothing but a compass needle. Okay. Have you all seen a compass needle? Yes, we have seen it. Okay, so how is a compass needle basically? It's nothing but a small needle which, if it is left, automatically it faces in the which direction? It is in the north-south direction. Okay. So the north of the needle is obviously pointing towards the north, and the south of the needle is pointing towards the south. So it is showing you the direction of the geographic north and the south. Now, when he was doing experiments with some other whatever he was working on, and when he was passing current through the wire, he found that there was a deflection in this magnetic needle or the compass needle. Are you understanding what I am saying? Okay, so there was a deflection. That means it no longer was pointing in the north-south direction, but it was getting changed. Further, he also noticed another thing. When he reversed the direction of the current, instead of passing it in one direction, if at all he is able to pass the current in another direction, what did he find? He found once again that there was a deflection taking place, but the deflection was in the opposite direction. Please stand up and tell me, what was Austin's experiment? No, don't have to look. You tell me. If you are paying attention in class, I'm sure you'll be able to tell. Tell me. Magnetic? What is happening? What's happening? Go. Sit in the last section. With your book, please. Whatever your books are, please take it away. And listen to me, okay? I don't want any confusion. With your back, please, Michael. Last bench. Last. Yes. It should. Yes. Tell me, Arush. What was the experiment and what did you make?
We observed that the data was no longer showing the north-south directions, and
What was happening to it? It was no longer showing. What was happening like this? There's a deflection. Okay? So there's a deflection. That means the needle, this is a needle which is coming under the influence of another magnetic field. Have you followed? So that was his observation. And instead of just throwing away the experiments, he started wondering as to why it was actually happening. So you will realize that most of the scientific discoveries are made not because by chance, because the scientists who were actually working on it had very keen sense of observation. Have you followed? This because of their inquisitive nature, they are following, they are finding out what is happening, and because of it, we started working on it. And now, of course, we are talking about the magnetic effects of electromagnetism. Electromagnetism. That's an entire huge chapter that we are going to be studying. And we also know that electromagnetism is present in almost everything that we are working on, whether it is a motor or it is a generator. And we know that these are the type of appliances and equipment that we are using in variety of our devices, which we are, day-to-day devices. Have you followed? Even a simple thing like your amplifier, ammeter, voltmeter, all these things are nothing but the magnetic effect of electric current. Have you followed? So it was a very, very brilliant discovery, and also it was basically because of his own observation. Now, for you to understand why is our magnetic needle pointing in the north-south direction? Let us say this is your compass needle, okay? And this is your east, and obviously this is going to be your west. Why is that the needle is pointing always in the north-south direction? Basically, when we are talking about this is the earth, and this is the geographic north. I'm talking about this is the geographic north, and this is your geographic south. Can anybody tell me?
Because we are facing towards it.
Because we are facing. Why should it point towards the north or the south? Tell me. No, you don't have to tell me. I'm asking you the question.
magnetic force of the earth.
Magnetic force of the earth. You're coming closer. You're on the right path. Not gravity. I'm talking about the magnetism. Yes, you had something to discuss.
Yeah, the same electromagnetic field
Of
of the earth.
earth. So what is happening?
It's in 2 points, not in the south. I tried poles, not those poles have these almost magnetical
Okay,
forces.
so we are talking about the geographic north. What is present in the geographic north?
Ice pole.
You're talking about the Arctic and the Antarctic region. Then those are the geographical features. Now I'm talking about the magnetic features of the earth. For you to understand the earth, okay, it is having a core of what is known as the outside portion is what is known as a mantle. And the inside part of it is core is nothing but a molten metal. Okay? And that's molten, right? So when we are talking, So when we are talking about the North Pole and the South Pole, let us consider that these two are, let's say, two bar magnets. Just consider that this is the bar magnet. Every bar magnet has got two poles. Okay? One is the North Pole. Assume that this part, cap part of it is the North Pole and this is the South Pole. What happens if we cut this magnet into two pieces? Will North go in one piece and South go in the other piece?
So pole will
Always
be
be
magnet.
together. Okay, so you will have two magnetic pieces. So suppose you have a north and a south, and let us say we cut it, you will have two small pieces, but each one of those small pieces will obviously have a north and a south. And so it's always a dipole, you should remember. Now my question is, suppose this is the north of one, and this is the north of the other. Okay. We are knowing something about repulsion and attraction. So if there are two like poles, two north poles which is coming to you, which will never attract. It is getting pushed. In fact, you must have actually seen the poles, right? There is no way that you can actually push them together because like poles will. Sorry. Yeah, you can actually feel the forces. You can actually feel, yes. What happens to if you're bringing both the souths together? Once again, both the souths together, like poles, once again it will attract. But if you get a knot,
It will attach to each other.
yes, it will attract. If you get a knot at the south, obviously there's going to be a magnetic attraction. Okay, so this in mind, I'm coming back again here. Why should a knot of a needle here go towards north? Okay, because we know that the earth itself is a huge magnet. Okay, because of the molten mass, the earth itself is a huge magnet. And what we are having in the geographic north is actually magnetic south. Do you understand? It is the magnetic south of the earth. So that is why this needle north is getting attracted towards the south. Do you understand what I am saying? This is the geographic south. Correct. This is your Antarctic region covered with ice and all that. But your south pole here, the south of the needle, is obviously has to get attracted towards the north. So this is the north of the earth, of the magnetic earth. If you are talking about the magnetic field of the earth, this is the north, that is why the south is pointing towards it. Okay? So every time whenever we talk about a magnetic needle, remember that your compass needle is nothing but a very fine magnetic needle which is pivoted. What is the meaning of the word pivot? There's a small needle here and it can freely move about. So that is basically what is known as a pivot. So if you're having a free suspended magnet and you leave it, automatically it will turn towards the north-south direction. Have you found out? Why is the north pole pointing towards the north? Is obviously because there's a south of the earth which is present there, which is pulling it. Did you get it? Okay. So basically we are surrounded by magnetic fields. But we don't understand it obviously because of the huge mass of the earth. But whenever we are talking about such type of magnetic field or even a lodestone, in the earlier days, the sailors used to use a magnetic lodestone, okay, which is to help them to navigate. So they did not have anything, they did not have your GPS or whatever it is. Only they had the North Pole Star, as well, of course, they had this lodestone which used to help them to move in the proper directions. Okay, coming back. Now let's look at something regarding what could be the properties of a bar magnet. So coming back to the basics, when we are talking about a bar magnet, right? We know that they come in different shapes. Okay? The most simplest, of course, are these bar magnets. Sometimes you find that there is a small coin like which we are using it as a fridge magnet. Small ones. Sometimes it's also present in the form of a horseshoe magnet. Why is it called as a horseshoe? Because of the shape. Okay, because the horse's saddle, the shoe part of it, is also protected by means of a horseshoe. So that's the tube shape. So it is coming in different shapes and sizes depending, and some of them are not only natural, some of them are artificial magnets. We'll see a little more here. When we talk about a bar magnet, we have already seen that it consists of a north and a south, right? And we know one of the most important properties is either a repulsion. We are talking about like pole, like and like pole, then obviously there's going to be a repulsion. But if you're talking about a like pole and an unlike pole, then obviously there's going to be an attraction. This is something that we have already seen. Further, how do we know what is happening? Suppose we take this as a bar magnet. How do we know that there's something here happening? Why is it that we are finding that there's a reflection taking place? Suppose this is let me talk about this one. This is a bar magnet. Imagine it is a bar magnet. You have kept it here. Okay. And this is your what? Needle, compass needle. Compass needle is of course very, very far. Right? Right now it is showing in the north-south direction. Why? Because it is under the influence of the Earth's magnetic field. But if I'm getting this magnetic needle closer and closer to this bar magnet, will it still be pointing in the north-south direction? Obviously, it will show that there's going to be a deflection. Correct? Assume that this is the north and the north is coming in this direction. What do you think is this?
South.
Isn't it? Obviously, because we know that unlike poles are the ones which are attracted. So if this is the north and if it is coming towards this, obviously we know it is the south. So that means to say this magnetic needle, or it is the compass needle, is coming under the influence of another field. It is no longer under the influence of the Earth's magnetic field. Okay? And this field is obviously felt when you're getting this bar magnet, the needle closer to the bar magnet. Is that okay? Is that clear? Yes? Okay. Now we have decided, or we have seen that there's some kind of a field which is present here. How can we actually make out what is the field like? So there's a very simple experiment. What do? We take iron filings. Okay. Filings, nothing but dust. Okay, fine pieces of iron filing. So we are having this bar magnet. We are keeping it on a sheet of paper. Imagine that we are performing the experiment, and we are going to sprinkle, okay, iron filings around. Iron filings, we know that it comes under the influence of the magnetic field. They are magnetic in nature, isn't it? Any iron pin or needle, if you take it near the magnet, it is going to attract. So gently I'm going to tap this. If you are tapping it, you find that it arranges in certain pattern. Did you see what that pattern is? See this page. Activity 12.2. What did you find? That these iron filings are arranging in certain specific pattern. Is that okay? What do these lines tell us? This tells us that this is the magnetic field lines, okay, around the bar. If you understand, it's very clear, isn't it? Further, if you look at the textbook, you can also see the pattern. What do you find at the poles? Is it the same pattern as you're finding here? What is it like? It is more crowded. Yes. So these patterns or the magnetic lines of poles, are you chewing gum? Oh. Basic knowledge you should have. So you find that it is getting more and more concentrated here. What does it tell us? What does it tell us? If it is more crowded, is it strong or is it weak? Strong. It's obviously strong. Okay. So we know that the magnetic field lines are more crowded at the poles. Therefore, we know that the strength of the magnetic field is more at the poles. Okay. What is happening to these? It's becoming bigger and bigger. As you're taking it away, it is becoming bigger and bigger. So these are concentric circles which is becoming bigger. Do they ever cross? Have you seen them crossing like this? One is crossing, the other one like this. It is crossing. Is it crossing like that? No, never. Okay. So these are what are known as concentric magnetic field lines, which never cross. What does it mean actually? Okay, why it is not crossing? Suppose we take once again coming back to our magnetic field, or it is a compass needle, right? This compass needle is very, very far away from that bar magnet. Once again, okay, as I'm getting, let us say it is pointing in the north-south direction. But as I'm getting it closer and closer, we know that there's going to be a deflection. Either it can get deflected like this, or maybe it is getting deflected like this. But immediately we find that it is coming under the influence of the magnetic field. One question I'm going to ask: what happens to the magnetic field as you are moving away from the magnet? Moving away from the magnet, what happens to the magnetic field? Will it decrease or increase? Decrease. Sure? Yes. So as you're coming closer and closer, the strength of the magnetic field will increase. You are coming closer. The moment you are coming closer to the bar magnet, the strength of the magnetic field will increase. Is that okay? Has everyone followed this much? I want you to be very thorough with this thing because constantly we will talk about the strength of the magnetic field. What happens when you are coming closer? What happens when you are going away? So, what are the various things that we have already learned about a bar magnet? For once, we have seen about like and unlike poles, how they are attracting, and next thing is we are talking about how can we actually find out the magnetic field around. As we are moving away, we find that these concentric rings are becoming bigger and bigger. Ultimately, it fades out. That means to say that we are moving away from the magnet and the strength of the magnetic field will increase. I want you to use the word strength of. It is not the magnetic field, it is the strength of the magnetic field which is increasing. Are you okay with that? Okay. Second thing is there is another figure on the next page. Can you see this figure? Okay. There's another method by which we can find out the direction of the magnetic field. What do we do here? Once again, we are going to take a bar magnet. Okay. We are going to take a small magnetic needle, a compass needle, and we are getting it across. Suppose you are keeping it here. Obviously, it is the north which is here, and that is the south. Okay. So we start from the north. It is the south, and it is the north. So we put a dot there. Once again, I'm going to move. Keep it here. You'll find that it is moved in a particular way. So I'm just going to keep a dot here. I'm going to keep it here. You will see that it has moved. And that is how I'm going to put all these dots and going to complete that circle, the concentric circle. Do you understand? By the direction of the north pole of the needle. Did you get it? So once I have all the dots placed, I'm going to join it. This will show you the direction of the magnetic field. Is that okay? Now my question. Yes, the question is, we have learned about the magnetic field. Is it a vector quantity or is it a scalar quantity?
I think vector because it shows direction.
Is it a vector quantity or a scalar quantity? I've given you two. Pick your option. Why? If you are choosing scalar, you should tell me why. If you are choosing vector, you should tell me why. Ananya? Why?
Because there is a specific direction.
Very good. Correct. Your answer was correct. Gaurav? You're right. Why? Vector shows it has magnitude, it also has direction. I've told you it is having a direction. It is the direction of the magnetic needle. So since we are also talking about the magnitude, we have already spoken about the magnitude. The magnitude is slowly decreasing, or the strength of the magnetic field is slowly decreasing when you are moving away. That means it already has magnitude. It is also showing you the direction. Since it's also showing you the direction, therefore we know that it is a vector quantity. Are you okay? Okay till now? Okay. Because these are the type of questions that can be asked for your 1 mark or MCQ or whatever it is. Have you followed? So there are two methods of finding out the magnetic field lines. One of them is by sprinkling iron filings. You tap it, it is going to arrange in concentric circles. The second thing is by using compass. Yes, you are using a small compass needle. The direction of the north pole you are going to keep on plotting it, and that is how you will be able to plot this. Is that okay? Clear till now? Yes? Okay, fine. I don't think right now I have that. Let me show you afterwards. Yeah, I'll show that afterwards. Fine. Let's read the book now. Come to the first page. In the previous chapter on electricity, we have learned about the heating effects. So now let's also talk about something else to understand that apart from the healing effect, it also has got magnetic effect. Who was the scientist who is considered to be the father of Ørsted? Ørsted. Okay, his Hans Ørsted, who is supposed to be the father of magnetic effects or electromagnetism, right? Who will be? I will be. Yeah, that's
In the previous chapter on electricity, we have learned about the heating effects of electric current. What could be the other effects of electric current? We know that an electric current carrying a wire behaves like a magnet. Let us perform the following activity to reinforce it. 12.1.
Now we'll do the 12.1 a little later because there's another experiment which will help us to understand. You see that one next one.
And then it is
Okay, read it, never mind.
Take a straight thick copper wire and place it between the points X and Y in an electric circuit, as shown in figure 13.1. The wire XY is kept perpendicular.
Skip that part, go to the scientist. We'll come back to this. Okay, because I have not yet explained that.
Hans Christian Ørsted, 1777-1851. Hans Christian Ørsted, one of the leading scientists of the 19th century, played a crucial role in understanding electromagnetism. In 1820, he accidentally discovered that.
Did you see that he accidentally discovered? Did you see that many accidents, accidental discoveries? That's what he saw. Have you heard about penicillin? Science too. Come on, biology, penicillin. What is penicillin?
Smallpox.
That is
Penicillin.
I think so.
What is it?
It's a vaccine for
It's
smallpox.
yeah, okay. Yes, it's an antibiotic. Okay. It's a very popular antibiotic, and that thing was also discovered quite by chance. Alexander Fleming was the one who actually discovered it, and it was quite by chance that he discovered it. Okay, so these are all through accidents, but of course, because of the keen power of observation of the scientists, they have been able to find out more about it. Continue.
That a compass needle got deflected when an electric current passed through a metallic wire placed nearby.
Underline that. What was happening here? You find that a compass needle is getting deflected when it is placed near a conducting wire. Okay, come on.
Through this observation, Ørsted showed that electricity and magnetism were related phenomena. His research later created technologies such as the radio, television, and fiber optics. The unit of magnetic field strength is named the Ørsted in his honor.
Okay, so the strength of magnetic field, the unit for the strength of the magnetic field is called Ørsted. Underline the word Ørsted. Okay, just as we are talking about ohm. Ohm is the unit for what? Resistance. Resistance. Okay, so Ørsted is the unit for the strength of the magnetic field. Okay, go on to the next page.
Magnetic field and field lines. We are familiar with the fact that a compass needle gets deflected when brought near a bar magnet.
Underline the word deflected because you have to use this word deflected. Go to the next page.
A compass needle is,
Yes, Ravi, next page.
in fact, a small bar magnet that the ends of the compass needle points approximately towards the north and south directions. The end pointing towards north is called north seating or north pole. The other end that points towards south is called south seeking or south pole. Through various activities, we have observed that like poles repel while unlike poles of magnets attract each other.
Underline these two words. Like poles repel, unlike poles attract. Why I'm making you write down all these things is the next question that you will be attempting to write is what are the properties of a bar magnet? Okay, for which you can use all these words. Yeah, which is this activity now. Yes, yes, we are going to read that. Anybody else wants to read? You want to read? Anish, read. Yes, yes, yes.
themselves in a pattern as shown. Figure 12.2. Why do the iron
Read activity.
activity 12.2?
Ah,
It's a sheet of white paper on a drawing board
Gaurav, book is in front of you. Ah,
using some LCD.
Adhesive material.
what is adhesive material? You are going to stick it on. Okay, so that the paper does not move. Adhesive.
Place a bar magnet in the center of it. Sprinkle some iron fillings uniformly
Filings.
around the bar magnet. A salt sprinkler may be used for this purpose. Now tap the board gently. What do you observe? The iron filling arranges themselves in a pattern as shown. Figure 12.2. Why do the iron fillings arrange in such pattern?
Iron filings. Filings. Not filling. Filing. See the spelling? Li. It's not filling. It's not double L. It's filing. Ah.
Experience of
Underline that. Therefore, it shows that the iron filings experience a force. What will be the question? Why do they arrange in a particular pattern? They are arranging themselves in a particular pattern because they are experiencing a magnetic field. They are experiencing a magnetic force.
the force thus exerted makes iron filings to arrange in a pattern. The region surrounding a magnet in which the force of the magnet can be detected is said to have a magnetic field.
Stop. Underline the word magnetic field. What is a magnetic field? Put a question there. Q. Okay. That means the region surrounding, did you get the answer? The region surrounding a magnet in which the force of the magnet can be detected is the magnetic field. Continue.
The lines along which the iron filings
Aligned.
themselves represent magnetic field lines.
Okay. Suppose you have to label this diagram. What are the things that you are going to label? What are the various things? Come on, label it right now. Many children who will not know what has to be labeled. Label it as bar magnet quickly in your textbooks itself. Bar magnet and those
Bar magnet.
and what are those? What will you
Iron
write?
filings.
Iron filings and you can also write it as magnetic field lines. Those are magnetic field lines. Done? Okay. Yes, Navi, you agree? Yeah. Are there other ways of obtaining a magnetic field lines around? Yes. Okay, so we are going to do activity 12.3. B. Yes.
Activity 12.3. Make a small compass and a bar magnet. Place the magnet on a sheet of white paper fixed on a drawing board using some adhesive material. Mark the boundary of the magnet. But place the compass near the north pole of the magnet. How does it begin? The south pole of the needle points towards the north pole of the magnet. The north pole of the compass is directed away from the north pole of the magnet. Mark the position of two ends of the needle. Now move the needle to a new position such that its south pole occupies the position previously occupied by its north pole.
Did you understand what they are saying? Okay. Step by step, this is what we are doing. We are taking a small compass needle. We are placing it here. Obviously, it is the south of the small compass needle which will point towards the north. So we are going to mark it here. Now this is north, this is south, this is north. So this is how we keep on, okay, moving or shifting the small compass needle such that it marks out the magnetic field lines. Continue.
In this way, proceed step by step till you reach the south pole of the magnet as shown in figure 12.3. Join the points marked on the paper by a smooth curve. This curve represents a
Field line. What field line? What field line is that?
Magnetic.
Put underline that. Just write it down as a magnetic field line. Don't get confused. It is the magnetic field line. Next.
Repeat the above procedure and draw as many lines as you can. You will get a pattern shown in figure 12.4. These lines represent the magnetic field around the magnet. These are known as magnetic field lines.
Magnetic field lines. I want you to use this word whenever you write your answer.
Observe the reflection in the compass needle as you move it along a field line. The reflection increases as the needle is moved towards the pole.
Underline that last line. The deflection increases as the needle is moved towards the pole. Put a quick Q there. Okay. Who can tell me what is happening? Why is the deflection becoming more when you're coming towards the pole?
And the compass get into the magnetic field of influence.
Okay, they're getting influenced by the magnetic field lines. My question is, why is it increasing as it moves towards the pole? Now, this is not the pole, right? It is somewhere away. Look at the board, everyone. It's somewhere there. But the moment I'm coming towards the pole, the deflection is taking place more and more. What does it tell us?
It is stronger.
Yes, it is stronger. Did you understand? Okay. Such type of most of the questions which is given in this particular chapter will be based on experiment-based questions. Okay, somebody is performing an experiment. He is finding something. You have to write down what the observation is and what is the explanation for that particular observation. That's why I'm stressing on those words because I want you to write down the correct words. Have you followed? So what will be the answer for that? Why is the deflection more when you're coming towards the pole? Because the strength of the magnetic field is more at the poles. Make a note. Make a note somewhere in your textbook. The strength of the magnetic field is more at the poles. What do you write? The strength of the magnetic field is more at the pole. Are we good?
Yes.
Here? Okay, fine. Now there's a diagram here. Once again, there is no labeling at all. Sometimes they will ask you to write down or draw the diagram with the labeling. What will you label?
The bar.
Bar magnet is one, magnetic field lines is another. Come on. Bar magnet and magnetic field lines. What is important here? What else will you write? What if I just draw this and leave it?
North pole.
What if you have to write the North Pole and the South Pole, correct? What else? What if a student draws only this? Will we give full marks?
The arrows.
Without the arrows, it's a 0 mark. Did you understand? We don't give any marks if the arrows are not there. How are the arrows?
From
From
north.
north.
Did you notice in the diagram? Very clearly they have given arrows are from the north, it is going to the south. So from the north to the south. Very, very important, mark it in your textbook. For the diagram, marks are going to be awarded only for showing the direction. Therefore, what does it tell us? Is it scalar or vector? It's a vector quantity. Make a note of it. Because it has got both magnitude and direction. Okay, therefore it is a vector quantity. Okay. Currently,
Yes. The relative strength.
now the okay, last part of your magnetic field is a quantity. Yeah, they're only there.
Yes, ma'am. Magnetic field is a quantity that has both direction and magnitude.
Underline both direction and magnitude.
the direction of the magnetic field is taken to be the direction in which a north pole of the compass needle moves inside it. Therefore, it is taken by convection that the field lines emerge from north pole and merge at the south pole. Note, the arrows marked on the field lines in figure 12.4. Inside the magnet, the direction of the field lines is from its south pole to its north pole.
Stop.
Thus,
Stop. Read that line again. Read the line again. Carefully read it.
inside the magnet, the direction of the field lines is from inside. So it goes like this.
Yes. So look at the board now. All of you understood? From the north pole, it is coming to the south pole.
Then again it is.
But again, it is going inside. From inside, it is from the south pole to the north pole. Therefore, we say it is a complete concentric circle. It's not cutting there. Have you followed? Once it comes here, this is the north. From the north pole, it is coming to the south pole, and continuing from the south pole to the north pole. So it is a complete concentric circle. Have you followed? Now, when you are reading the question, you have to be very careful, because sometimes they will give you the direction of the magnetic field from south to north. Is that correct or wrong?
South and
Inside the magnet,
correct.
the magnetic field lines are from south to north. Perfectly all right. So you have to read the question very carefully. Did you understand? Okay, fine. You will also find some things like this. Half of them are like this. Why is it half like that?
Because it is complete.
Yeah, actually we keep on going, no? Itna bada bada chale jayega. So just to show you that it is still there. It is coming from somewhere like that. We are not drawing all the field lines. We are just showing two of them, and the rest of them are still coming. Did you get it? Okay, fine. Very good. See?
Thus, the magnetic field lines are closed curves. The relative strength of the magnetic field is shown by the degree of closeness of the field lines. The field is stronger, that is, the force acting on the pole of another magnet placed is greater where the field lines are crowded.
Crowded underline. Okay, your field lines are crowded where? Is it away from the magnet or closer to the magnet?
Closer to the magnet.
Where? Which part of the magnet?
In the north and south.
Poles, near the poles. Okay. So the magnetic field lines are crowded at the poles. Therefore, it shows that the strength of the magnet is more towards the poles. Okay. Continue, please.
No two field lines are found to cross each other. If they did, it would mean that at the point of intersection, the compass needle would point towards two directions, which is not possible.
You understand? We have already spoken about this. We find that these are all concentric circles. You will never have any line which is crossing over like this. It is impossible. Why? Because whenever you keep a magnetic needle here, obviously it is not showing in two directions. You cannot have two directions, right? So therefore we can easily make out that it is not intersecting and it is only concentric circles which are present. Are you okay with that? Okay. It may sound very simple for you at this stage, but when it comes to writing down your answers, I don't want anybody to make a mistake. Have you followed? If you don't use the word the strength of a magnetic field, again it will be lost. Half mark, you will lose the entire way. That's why I'm insisting again and again, I'm telling you what are the important points. You should write, it has got magnitude and direction, it's a vector quantity. Be careful to show those arrow marks when you're drawing. Okay. Sometimes an incomplete diagram is given to you and you will be asked to complete it. Okay, so you must know what is the correct diagram and so on and so forth. Very good. Come on, let's write down a few points now. In your notebook, chapter number 12. Okay, magnetic effects of electric current. Date your work. Put your date. What's it? 12.
Yes.
Today's 12. First one. We start writing about the scientist mentioned, Hans Christian Ørsted. put a small hyphen and write, showed that electricity and magnetism are related phenomena.
Now we have to write like the meaning of the
As Orsted, if you write, I want you to remember Orsted. What did he show? He showed that electricity and magnetism are related phenomena. That's all. I don't want you to remember anything else. Anish, are you writing? Start writing fast.
magnetism are related.
Electricity and magnetism are related.
Are related for
Phenomena.
phenomena.
Second point. The unit of magnetic field strength. Next point. The unit of magnetic field strength is named Austin. Once again, can we ask for your MCQ? Next question. What are the properties? What are the properties of the magnetic field lines?
Properties of
Magnetic field lines. Raj, what is your answer? What is the properties? These field
like a
lines.
specific shape, like
So you will write shape. What will you write? What are the words that you should use?
Connected from North Pole to the South Pole.
Okay, very good. Directions. Yeah. They never intersect. Yes. What else?
Both the poles have equal strength.
it is a vector quantity.
Vector quantity. Fine. Magnitude that comes under them. Talk about the poles. What is happening at the
Both
poles?
the poles have the equal strength.
Not equal strength. I did not say equal. More. Yes. Magnetic field lines are crowded at the poles. Yes.
Equal pole.
Okay. So there, obviously, the strength of the magnetic poles are more. What did you say?
They are continuously.
Concentric circles. Use the word concentric circles. Come on, write the first point. Magnetic field. And all the points are there in this paragraph. Look here. We have just read it, this paragraph. Okay. Magnetic field is a quantity that has got both magnitude and direction.
Some we can be like vector and bracket.
Yes, you have to. For you to remember, vector has to be.
So magnetic field is a quantity.
Direction. Yeah. Direction and magnitude. Direction and magnitude.
Anish, you have your textbook, no?
Yes.
Then first line there. Can we read the textbook, please? Next point, what will you write?
Direction and
Can you write about the direction? What will you write?
The direction
One
of
line.
the south.
Yes, all of you write down. The direction of the magnetic field is from north to south pole.
Inside it.
Inside it, in the same point you will write. Inside the magnet, what will you write?
It is from south to north.
What is that heat? What is that?
Magnet.
No, magnet is not. The direction of the magnetic field. Did you see that? The word direction is so important.
Inside the direction.
Inside the magnet, the direction of the magnetic field is from south pole to north pole. Next point. Inside. What did you write? Inside the magnet, the direction of.
The direction of magnetic field is from north to south pole inside the magnet.
Inside the magnet is what? It's from south to north. See here. This is the bar magnet. Outside, how is it? From north to south. But inside, how is it? It is from south to north. Okay. In the same point, you will write. Thus, the magnetic field lines are closed curves. Anish. Thus, the magnetic field lines are closed curves. Okay. Next point, what will you write? What's happening at the poles?
Poles are ground.
Magnitude will be the same.
The same type of
Yeah.
lights.
Yeah. Next point, what will you write, children?
The lines do not cross each other.
Now you talk about the relative strength. What's happening at the poles?
It's a crowded.
More crowded. So what does it show?
If the magnet
The strength is more. Come on, write down. The relative strength of the magnetic field from your textbook only. Take the point from the textbook. The relative strength of the magnetic field is shown by the degree of the closeness of the field lines. Closeness of the field lines. In the same point, you will write the magnetic field is stronger at the poles. The magnetic field is obviously where is it stronger?
Poles.
At the poles. Ah. What will you write about the last point?
It has both directions.
That we have already finished. First point was that. Yes. We are talking about the lines which are never going to intersect. Last point. No two field lines cross each other. No two field lines. When I use the word field lines, it obviously means it is a magnetic field. They do not cross each other. If they did, I know, if they did, it will mean that at the point of intersection, the compass needle would point towards two directions. which is not possible.
Which is
Not possible. Is that okay? Okay till now. Go to the next page. And to the next page. There is a set of in-text questions. Go to this page. First question is draw magnetic field lines around a bar magnet. Okay, which you are going to do now. Second question, list the properties which we have just done now. Put a tick mark for the second one. This one is first. Second question is done. Okay, the third one. Why don't two magnetic field lines intersect each other? Yes, that is what we have already written in the last one. Is that okay? So we have completed question number 2 and 3. I'm just giving you 5 minutes time to quickly do the first question. I'm going to come around and check what you have done. Yeah, it's without talking, you're going to draw and label it also.
We can do the bar magnet as well.
Should fit no whatever it is. Don't mess with it. What do you do? No, what do you want? You want it to be closed? What is it?
we don't want it close, but we have to reduce the mass.
Why don't you shift? And if I said only 5 minutes to complete the diagram.
Array platform.
Ah, yes.
At the bottom. But
Come on. I'll Which question are you doing now?
This one.
Index the first.
This A and low is
Label. Labeling. Try as far as labeling, Kushika, labeling, if at all it is possible, do it in capital letters. Labeling, do the name. What are you waiting for? No need, everybody is waiting for us. Yeah. Raj, don't need of so many lines, just 2 lines for representation, that's all.
Good.
So, label. What else? Nothing is given in your textbook, but I told you how to label what has to be labeled. Make sure that it is from north to south. 2 is enough. 2 lines, 2 above and 2 below is more than sufficient for you to show that you have understood the concept. Now, I don't want anybody to lose out marks with diagrams. Remember in light, what did I tell you? Incident ray, reflected ray or refracted ray, you should always show those arrowheads. In both directions, do not appear. If you are showing 2 on one side, it will make symmetric. You show 2 on one side and 2 on this side. Even this also. See this side of the bar. Make the diagram as symmetric as possible, right? Okay, now let's write down this question now. Done? Everybody has finished? Okay. Next question. Arush? Ayush, here. Question number, first one on page number 196. Why does the compass needle take down?
I'm going to write the question.
How will you know? Unless of course you want to put it as page number, question number. Why does a compass needle get deflected? Why does it get deflected when brought near a bar magnet? Can you understand the question? Why does the compass needle? Now let us say that this is, and look at me everyone. Let us assume that this is a small compass needle. Okay, it is ordinarily showing north-south direction. But the moment it is coming closer and closer to the bar magnet, it is getting deflected. Okay, the question is, why is it getting deflected? What will you write?
When electric current passes.
Approximately towards now. Then.
Okay, what else will you write? What did you say?
Electric current
Magnetic
passes.
force.
Where is the electric current now?
That is
The
not
magnetic lines attached with the bar magnetic.
Magnetic bar.
The magnetic
Force. What's happening?
on the magnetic force attracts
What is this?
light pole with light.
This itself is a compass needle is nothing but a small bar magnet, which has got a north and a south end. Right? And that is why it is naturally pointing in the north-south direction. But when it is brought closer to a bar magnet, it is coming under the influence of the magnetic field lines, and therefore it is getting deflected.
Light and light so that each other and
It's getting deflected if you write it. Come on, write. Start. Come on, write on everyone. I'm not dictating. First, talk about what this is, what it has. How is it under normal conditions? What is a compass needle? What is a compass needle? It's a small bar magnet, first point. A compass needle is a small bar magnet. How do these ends point? Yeah. Second point is the ends of the compass needle point in the north-south direction. Arush, third point, what will you write? Oh, right. Raj, what will you write third point? Thinking. Now the third point is when it is coming closer. What is happening?
when it comes to it reflects
Because it is coming under the influence of the magnetic field. Come on, write it.
Let's repeat the second one.
What did I say about the second point?
the ends of the
The ends of the compass point to north and
Points in the
south.
north-south direction.
Ma'am, do we have to describe this also the end pointing towards north is called north seeking or north pole?
It depends upon the marks. Usually such type of questions are asked for 2 marks.
So we don't have to write. So directly we can write in the
Third point, when a bar, sorry, compass needle is brought closer to the bar magnet, it shows a deflection. It shows a deflection because it comes under the influence of the magnetic field of the bar magnet.
Because it comes under the
Influence of
magnetic field. Now it's under the force of magnetic field.
yeah, you can also use. Comes under.
Ma'am, like opposite weather.
Yeah, there you can write. Last point you can write down. Like poles repel and unlike poles attract. Repel. Like poles is what? Both north or both south. Repel, R-E-P-E-L, and unlike poles attract. Okay, come to the last page here. I want you to go to the first 3 points. Put a tick mark for the first 3 points. Raj, read first point.
A compass needle is a small magnet. Its one end which points toward north is called a north pole, and the other end which points toward south is called a south pole.
Next.
Magnetic field exists in the region surrounding a magnet in which the force of the magnet can be detected. Field lines are used to represent the magnetic field. A field line is the path along which a hypothetical free north pole would tend to move. The direction of the magnetic field at a point is given by the direction that a north pole placed at that point would take. Field lines are shown closer together when the magnetic field is greater.
Okay. So all these 3 points is what we have learned now. Okay. This is, you have to be thorough because when we talk about a solenoid, we say a solenoid is behaving exactly like that of a bar magnet. Okay. So that is how we are able to compare both the solenoid as well as the bar magnet. Right? Did you understand? Here till now? Okay, right? So far, we have been talking about a bar magnet, and we have seen what are the characteristic features of the magnetic field around a bar magnet. Okay, there's a very interesting experiment that we are going to see now. It's regarding what happens if you are having a conducting wire. Suppose this is a copper wire. Okay, and in a copper wire we are passing current. Look at the direction. See how I'm showing you. Like this. Correct? So the current is flowing in this direction. Or I can show it in this way also. Direction is very important. So how is it going? It is going in this direction.
Ma'am, that blue one is not.
No, it's only a copper wire. It's not a magnet at all. I'm just showing you how the direction can be changed. Right? So depending upon it, what did Oersted find? He found that whenever there is a current which is flowing in a conducting wire, this wire develops a magnetic field around. See the direction, how I'm showing you, in this direction. That means you will find that there are concentric rings around the conducting wire. In which direction? Perpendicular to. Have you followed what I am saying? If this is your conducting wire, the field is developing in a direction which is perpendicular to the direction of the flow of current. Did you understand? What happens to it? As you are moving further away, what happens to the strength of the magnetic field? When you are coming closer, what will happen? When you are going away, what will happen?
Push.
The strength of the magnetic field increases when you are away.
Oh,
When you are coming closer, what happens?
Increases.
Don't say increases. What is the word that you should?
Stronger.
The strength of the magnetic field becomes stronger or it increases. Are you okay? Now, how do we actually find out that it is becoming more or less? For that, there is a very simple experiment. Force on a current carrying conductor. Was required. Did you see what's happening now?
From the currency.
Right. Okay, he was the one who actually found out. Yeah, I am pausing it here so that you understand what the experiment is about. Right? We have taken the cardboard. Did you see that? And we have taken this wire such that it is passing through the cardboard. Correct? And it is connected to the battery. Now this is the positive and this is the negative. So in what direction will the current pass? From
Positive
positive
to negative.
and to the negative. Are we clear about that? Direction is very, very important. Now on this cardboard, what are we going to do? Once again, you are going to sprinkle some iron filings. So let's say we are sprinkling iron filings. That's basically your cardboard here. Right? See the position. Now what are we doing here? Iron filings. You sprinkle some iron filings. And you are gently tapping it. See the direction here, coming from the positive to the negative end. Did you see that? See the direction? Or now I'm pausing it once again. Did you find some direction here? Did you see the arrowheads?
Yes.
Okay. So that means to say you will be able to find out the direction of what? What is this direction of? The magnetic field around the current carrying conductor. What are the words? This is a current carrying conductor. It's a conductor in which current is going. And this basically shows you the direction of the magnetic field. And this is given by a very simple statement which is called as a right hand thumb rule. And that's basically what we are going to learn the next video. Got it? Lovely. Before even we go on to that, I'd like you to understand what is known as a right hand thumb rule. Look at me. Right hand, right? Right hand and thumb rule. So hold the pencil in your pen or pencil in your right hand. Hold it in your right hand such that the tip is pointing in the direction of your thumb. Tip of the pen or pencil is pointing, right? So the thumb is pointing in the direction of the current, and your curled fingers here is pointing in the direction of the magnetic field. Did you understand what I'm saying? So it's going like this. Is it clockwise or anti-clockwise? Like this. Anti-clockwise with respect to the direction of the current. Now see what is happening. I am putting it down. What does it tell us? That this is the direction of the current. Now did you notice how it is going?
Yes.
If the current is flowing down, the direction of the current magnetic field line is going. But it is always with direction, with respect to the direction of the field. What happens if we keep it like this? How is the current going? I'm standing this way. From east to west. I'm talking about. So this is going from south to north. The direction of the magnetic field is from south to north. Okay, what happens if I'm keeping it like this? Once again, this is the direction of the current. But how is the magnetic field lines coming? It's coming from north to south. Have you followed all that? Okay, so what rule is this? What is rule? Right hand thumb rule. Don't get confused because there's also another which is known as Fleming's left hand. Yeah, there's a Fleming left hand rule. Don't get confused. So that's why I'm saying right hand.
And there is
thumb
two
rule.
limits left and right.
But in your latest syllabus, they have cancelled the right hand. Then it's right hand has been cancelled. That is for generator. That's not there in the text. Is that okay? Right. Now let's leave that thumb rule before we start. We still have a few minutes.
2 minutes.
Yeah. Did you see this? Twice? Yeah. Right hand.
Yes.
Okay. Nice.
Yes.
Right hand thumb rule.
190. 190.
Last.
A convenient way to find the direction of magnetic fields associated with a current carrying conductor is given in figure 12.7. Imagine that you are holding a current carrying straight conductor in your right hand such that the thumb points towards the direction of current. Then your fingers will wrap around the conductor in the direction of field lines of the magnetic field as shown in figure 12.7. This is known as the right hand thumb rule.
Okay. This is basically what is known as a right hand thumb. So, there's a small asterisk there. It's also known as Maxwell-Cox rule. We'll carry on. Check. One more day, we'll see how the behavior changes or not, and then we'll decide. Okay? This rule holds for everybody here. For everybody.
अबे सब मत जाओ ए राजू
दो मिनट रुको जिसको भी वॉशरूम यूज करना है वो कर ले क्योंकि फिर कभी में काम शुरू होने वाला है एक तो बंदे का साथ में चलेगा फिर बोलना नहीं कर दे आपको
क्यों बोल रहे
आ जाओ हेलो हाँ बोला सुनिए ना आप लोगों ने कि हाँ बाद में किसी के मुंह से कंप्लेन नहीं चाहिए मुझे लेकिन अगर गलती से तेरे मम्मी को आ गया बहुत आ गया दोनों झाड़ है चल पीछा लगा चल पीछे पागल हो गए भाई अरे राज को मुझे तो भाई सही ले जा हेलो राज नहीं हेलो राजू भाई बोलो हेलो भाई यार नंबर दे दो हेलो सो अलग ही है कोई छींकने में तो हर में नाम ला रहा है क्यों अरे क्योंकि मेरी बहन ने मेरे घर का नाम है
मेरी छोटी बहन को हम सब लोग छोटी
नहीं अरे क्या है मेरी बहन बचपन में वो डॉल से खेलती थी उसका नाम बहुत फेमस है उसका डॉल उसका नाम अच्छू था मेरी बहन का पहला मेरा नाम अच्छू रख दिया भाई
तो खुशी की बात है ना तो डॉल है
खुशी की बात है भाई
मेरे बातों में इंटरप्रेट करते हैं
एक्सटेंडेड फैमिली मेरा मतलब वी आर इन एक्सटेंडेड उनको मेरा रियल नेम विरोधी करके पता ही नहीं है उनको मेरा भी नहीं पता सबको को भाई
कोई ज्यादा सब खुशी खुशी बोलते हैं तो इसके लिए मैंने काम कर दिया था खुशी के उस पे क्योंकि अब सुनने की बहुत आदत हो गई थी कि रोजना मेरे करता था मैंने जैसे ही नाम बदला अपना यूजर नेम आईडी का इतने सारे फॉलो रिक्वेस्ट आ गए मैंने बोला कहां से आ गए भाई
क्योंकि लोगों को तेरा खुशी ना
हाँ
एग्जैक्टली तो शिट नहीं करते वो मेरा फोन देखो राजू लेके चला गया
तू यहाँ से आ
हाँ
करीब
डायरेक्ट ऐसा कर दो दिया है
ये ये
मुझे लोग कौन बोलते हैं कि ना
ना
आपको ना देख यार तो बात में अगर बोल करता है बात बोलना में नहीं करता रहेगा बात में बोल दो मैं बोलूंगा ना
सारा ठीक है हाँ ना कौन बोलता है बोल रहा है तुम्हारा हड़वाई है नेक्स्ट क्वेश्चन बड़ी हड़वाई ओह माय गॉड सर
अबे हमारे स्कूल में क्या क्या चलता है बेंच टॉप चलता है क्या क्या नहीं चलता भाई गालियों को ना चूड़ियां बोलते हैं तो चूड़ियां है भाई तूने मतलब वो
बस
चूड़ियां एक तो पीयू को गाली पसंद नहीं जो मेरी फ्रेंड है उसको गाली पसंद नहीं तो उसके सामने आप गाली नहीं दे सकते आपको बोलना पड़ेगा या तो चूड़ियां बोलो या तो चुईया बोलो
मैं बोलना बता दूं मुझे तो लगता है
क्या करते हैं
शब्दी है जो भाई नहीं आप प्लीज मेरे सामने गाली मत उसको उसके पैरे भाई तू बहन जो भी है भाई ऐसे लोग होते हैं
तेरा टप्पा
हम लड़की का पढ़ते हैं
हाँ बोलो
लाड़ी